Welcome! So if you're diving into calculus, you already know that limits are, well, everything. They're the foundation. Today, we're going to build your ultimate toolkit for tackling limits with algebra. So let's open it up and see what we've got. You know, in a perfect world, finding a limit is just simple. For most of the functions you're going to meet, like your everyday polynomials, you can use what's called the direct substitution property. You literally just plug the number a into the function and bam, that's your limit. Easy, right? But it's not always a perfect world.
Because sometimes, when you try that direct substitution, you get this, 0 over 0. Now, I know your first instinct is probably to think, oh, it's undefined, or maybe I messed up. But in the world of limits, this is something else entirely.
Getting 0 over 0 is what we call an indeterminate form. And it absolutely does not mean the limit doesn't exist, not at all. Think of it like a signal from the function. It's basically telling you, hey, hold on, there's something more interesting going on here. You just need to do a little bit of algebraic detective work.
And of course, for any good detective work, you need the right tools. So we're about to open up our algebraic toolkit for limits. This is a set of really powerful techniques designed for one specific job, to solve that 0 over 0 mystery and find the real limit hiding underneath.
First up, we've got the factoring method. This is your go-to, your number one tool anytime you're dealing with a rational function. You know, a fraction with polynomials, and it gives you that 0 over 0. It's usually a dead giveaway that there's a tiny hole in the graph, and factoring is how we're going to find it. Okay, let's look at this classic example. If you plug in 2 right away, you get 4 minus 4 over 2 minus 2. That's 0 over 0. So we pull out the factoring tool. The numerator, x squared minus 4, that's just the difference of squares, right? It becomes x minus 2 times x plus 2. And look at that. We have a common factor of x minus 2 on the top and bottom that we can cancel out. And we can do that because a limit only cares about what's happening near x equals 2, not at x equals 2. Once that's gone, we're left with a much simpler expression we can finally work with. And just like that, we plug in our 2 and we get the answer. The limit as x approaches 2 is 4. We basically just figured out the y value of that little hole in the graph. All right, so what if you can't factor? What if you see a square root in there and you're still getting 0 over 0? Well, that's when we reach for our second tool, the conjugate method. This is a really clever trick to sort of restructure the problem when radicals are involved.
Let's walk through this one. Again, direct substitution gives us 0 over 0. No good. The trick here is to multiply both the top and the bottom by the conjugate of the numerator. That just means you take the expression and flip the sign in the middle. When you do this, it's kind of like magic. The numerator simplifies into a nice polynomial that we can factor, and what do you know? A t minus 4 term appears, which is exactly what we need to cancel out the term in the denominator that was causing our 0 over 0 problem.
So after we cancel and plug in 4 for t, the math works out, and we land on our limit, -5/8. The key takeaway is that the conjugate method changes the form of the problem so we can actually solve it. Our third tool is for those really messy-looking problems, a complex fraction, where you've got little fractions living inside a bigger one. The goal here is just to clean it all up, to turn that complicated beast into one simple fraction. Let's see how it works. First, just focus on that top part, the numerator. We find a common denominator and combine those two little fractions into one. When you do the algebra, something really convenient happens. A negative x pops out on top. And this is why the method is so great. That x is precisely what we need to cancel with the x in the main denominator, which was the whole reason we were getting 0 in our 0 over 0 problem to begin with.
With that problem-causing x now gone, we can safely plug in 0 and find our limit, which turns out to be -1 over 16.
Okay, let's switch gears a little. All our tools so far have been about algebraic tricks, factoring, multiplying, simplifying. But what happens when no amount of algebra can fix the problem? For those cases, we need a different kind of tool, a more conceptual one. We need the squeeze theorem. The idea here is actually pretty beautiful and really intuitive. Imagine you've got a function f of x, and it's always trapped or squeezed between two other functions. Now, if you know that those two outer functions are both heading towards the exact same y value, L, well, where else can the function in the middle go? It's got no choice. It's forced to go to L too. So this is the all-star example for the squeeze theorem. That sign of 1 over x part just oscillates like crazy as x gets close to 0. Algebra is useless here. But we do know one thing about the sine function, no matter what's inside it. Its output is always trapped between -1 and 1. That's our starting point. So we take that simple fact, that inequality, and we multiply the whole thing, every single part, by x squared. And since x squared is always positive, we don't need to worry about flipping any signs. Just by doing that, we've successfully built our squeeze. We've trapped our complicated function between two much simpler functions, negative x squared and positive x squared.
And here's the key. We can easily find the limits of our two squeezing functions, right? The limit of negative x squared as x goes to 0 is just 0. And the limit of positive x squared as x goes to 0 is also 0. They're both heading to the exact same spot.
So what does that mean? By the squeeze theorem, our original complicated function that was stuck in the middle has to have a limit of 0 too. It literally has no other choice.
So we've covered factoring, conjugates, complex fractions, and the squeeze theorem. But why does all this matter? What's the big picture here? Well, these aren't just random algebraic puzzles. These are the skills that unlock basically the entire rest of calculus.
This toolkit, factoring for wholes, conjugates for roots, simplifying fractions, and the squeeze theorem for the impossible stuff, this is what lets us properly define things like continuity and, more importantly, the single most important concept in Calc 1, the derivative.
And here it is. Here is the real aha moment. That squeeze theorem, which might have seemed a little abstract or weird, it's actually one of the unsung heroes of calculus. It is the only way we can formally prove one of the most fundamental limits involving the sine function. And without that proof, we could never figure out the derivatives for sine and cosine. And without those, a huge chunk of physics and engineering would just fall apart. It's that important.
Look, mastering these tools is absolutely crucial. But calculus always has another layer, another puzzle waiting for you. Which kind of begs the question, right? What happens when even these powerful algebraic techniques aren't enough to solve a 0 over 0 problem? What comes next? Well, that's a story for another explainer.